Okay, welcome back to Precalc C. Over the weekend, you had a bunch of counting homework problems, and yeah, like I said, they're either sort of really easy for you if this kind of comes naturally, or if you have some experience with this. But some people struggle with it. It's kind of hard, and maybe you don't know the precise way to think about these problems, so it's important to do all of them. All right, in a normal class, I would go over like all the problems, but this seems like just kind of too much, so I went over a selection of them in class very sort of slowly and carefully. All these ones with an X through them are the ones that we did in class on Monday and Tuesday, or at least those are the ones that we did in every class. So this was every problem that was assigned. I'm going to do the circled problem. So I'm going to do 3 problems that are maybe relatively easy, and then I'll go on to a couple problems that are quite hard, and then at the end there are these kind of 2 proofs. Okay, so let's go. Hopefully this will be enough for most people, but I'm also willing to help you if you have some questions on those early ones. Okay, number 11. Here we go. Number 11 says, how many 3-digit numbers can be formed under the following conditions? And alright, so I'm looking at 3-digit numbers. Well, the leading digit cannot be 0. That seems just like built into the definition of 3-digit number. If someone asked you for a 3-digit number and you gave them like 043, you know, they'd probably give you a look like, dude, that's just not a 3-digit number. So, alright, so part A is really just kind of asking, you know, how many 3-digit numbers are there, in my opinion. And, well, this, I think, is easily done, because if the first digit can't be a 0, then what can it be? It can be any one of the numbers 1 through 9. So I have 9 choices for what to make the first digit, but then I have 10 choices for what to make the second digit, and I have 10 choices for what to make the third digit. So since each of those choices is independent, that gives me 900 total answers to this part A. And of course that makes just complete sense, that there are 900 3-digit numbers from 100 to 999 inclusively. When you subtract, you get, you know, 899 plus you add 1 because inclusive. Okay, so that's just the right answer, and also duh. Part B, the leading digit cannot be 0, and no repetition of digits is allowed. Okay, that's kind of interesting. So now I have, again, 9 choices for the first digit. It can be anything except 0. And then how many choices are there for the second digit? Well, now you have not quite all 10 digits available, but only 9 of them, because you can use any digit except the one that you used the first time. And then for the third digit, you can use, you have 8 choices, because you can use any of the 10 digits except the one you chose first and the one you chose second. Okay, so the answer to this problem is whatever 9 times 9 times 8 is. Maybe I shouldn't put dots here. Well, maybe I should. Okay, part C. Part C. The leading digit cannot be 0, in other words, it's a legit 3-digit number, and the number must be a multiple of 5. Okay, well, if the number must be, okay, well, if the first digit can't be 0, then there are 9 choices, once again, for the first digit, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if the number must be a multiple of 5, well, okay, this is just a math fact that the only numbers that are divisible by 5 are numbers which end in 0 and 5. So I have really just 2 choices for that final digit, but I can choose anything for this middle digit. And so what I actually get is 450. And yeah, that's more, no, that's not right. Oh, yeah, wait a second. 9, no, that's just the wrong multiplication, and it was the wrong answer. That's 90 times 2 is 180. Okay, that seems about right, because if there are 900 numbers, 3-digit numbers, then 180 is just 1/5 of them. And I think like 1/5 of the numbers are multiples of 5, because, yeah. Okay, final part D. The number is at least 400. Okay, well, if the number is at least 400, then that means the leading digit must be 4 or up. So what can the leading digit be? You know, 4, 5, 6, 7, 8, or 9. So you have 6 choices for the first digit, but then you have fully all the remaining available choices for the other digits, and so this is just 600, and you might say, Dude, of course, there are 600 numbers which are 400 and up. Again, it's all the 3-digit numbers between 400 and 999 inclusively is 600. Alright, so maybe we didn't need to do that problem. I mean, I think, you know, not to be like mean or whatever, but I would call this like a middle school math team problem. So, there it is. And you know, we should get smart so we can beat those middle schoolers, you know, at math team. Okay, 15. What does 15 say? Concert seats. 3 couples. Oh, I went over this problem in one class, but not the other 2, because someone asked about it. 3 couples have reserved seats in a given row for a concert. In how many different ways can they be seated if? First question says there are no seating restrictions. Okay, so 6 people go to a concert, a seated concert, so like, you know, classical music concert or something maybe. And these 6 people are all going to sit down. Well, in fact, there are 3 couples. And normally couples like to sit together, but okay, in part A, you know, they're just all friends with each other, and so they're all not necessarily going to sit with their partner, so they can just sit with whatever they want. Well, if they can sit whoever they want, then they're really not couples at all. They're just 6 people. And how many ways can 6 people be seated? There are 6 choices for who sits in the first spot, 5 choices for who sits in the second spot, and in general, 6 factorial is just the answer to how many ways can 6 people arrange themselves in 6 different places. It's the number of permutations of 6 objects. In this case, the objects are people. Okay, but part B is asking the question, well, what if the couples want to sit next to each other, as couples do? Okay, well, if the couples are going to sit next to each other, then you have to divide this up into kind of 2 smaller problems. Step 1, imagine that there are like 3 sort of couple boxes. And the 3 couple boxes are going to contain the 3 couples. And so, like, decision number 1, you know, which couple is going to sit where? This is, I think, quite reasonable, right? One couple is going to sit on the left, one couple is going to sit in the middle, and one couple is going to sit in the right. Well, how many ways are there to decide which couple sits where? Well, if there are 3 couples and there are 3 couple spots, then there are 3 factorial ways to do this. But once you've decided which couple sits where, you haven't actually finished the problem, because then as the first couple goes to sit in the first couple spot, they have sort of 2 choices about how they want to align themselves. Like, they can go jom or whatever. So there are still going to be 2 choices for what that couple does, and then this couple also has 2 choices for how they position themselves, and this couple also has 2 choices. And I am multiplying these numbers kind of without even thinking about it, or at least without talking about it, because I'm so experienced, but I think it is important when you're a beginner to articulate, at least in your own head, you know, what is it that is convincing me that I should be multiplying all these numbers that I'm mentioning. And the answer is the multiplicative principle. So the multiplicative principle, so this is the low level kind of logic of this, which you might need or you might not need. There are 3 factorial ways for the 3 couples to decide which couple sits where. For every one of those ways, there are still 2 ways for the first couple, for the couple sitting in the left spot, to sit down. For every one of those ways, there are 2 ways for the middle couple to sit. For every one of those ways, there are 2 ways for this one to sit. So the multiplicative principle really is at play. If you think of it as a branching kind of diagram, this is what I showed in one class. I won't redraw this now, but right there are 6 ways for the couples to sit down, and then the next decision you have to make is you know, the order of the couple on the left. So that branches, everything now doubles. So now there are 12 choices. But then for every one of those 12 choices, there are 2 more choices as to what happens to the middle couple. So that's 24. And finally, the third couple. Okay, so I won't go into this low level of detail, but that sort of explains once again why we're multiplying. Anyway, that's 6 times. What is that? 6 times 8, so that's 48. I might have been, no, yeah, that's right. So yeah, 6 times 2 times 2 times 2. Okay, good. That was 15. I think 16 is kind of like the same problem, but a little bit harder. Yeah. So in how many orders can 3 girls and 2 boys walk through a doorway single file? Okay, so here we go. All right, so old textbook. So anyway, so three girls and 2 boys. Okay. La 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 la. And they're gonna walk through a doorway single file. Okay, well if they're gonna walk through a doorway single file, then we're really just saying that they're gonna line up and they're gonna kind of go in order. So how many different ways can we line up 3 girls and 2 boys? Well, in the first case, part A, there are no restrictions. And if there are no restrictions, then really the fact that they're boys or girls is irrelevant. And so they're really just 5 people, 5 kids. And how many ways are there for 5 kids to get in a row? Answer 5 factorial. Okay, so that's pretty straightforward. But suppose for some kind of reason that you want the boys to go first. Well, if the boys are going to go first, then, you know the 2 boys are going to go first. Well, then you have 2 choices, right? The 2 choices are which boy goes first and which boy goes second. And having decided which boy goes first and which boy goes second, you then have to order the girls. And there are 3 girls, so there are 3 factorial ways to order the girls. And so the answer is 12. Here, 5 factorial is 120. Yeah. And 2 times 3 factorial is 12. Okay, and now what if the girls go before the boys? Okay, this is actually kind of a silly problem. If the girls go before the boys, then you just order the girls. There are 3 factorial ways to put the 3 girls in order, and for every one of those ways, you then order the boys, and so it's also just 12. Okay, good. Not sure we needed even to go over any of those, but maybe some people needed to. Okay, let's do this 48, which I think is just so hard, this number 48. And I have my notes somewhere, so hopefully I don't mess up my arithmetic. I have it written down somewhere, but I think I'll just do it from scratch. Okay, this is a good example of a really hard problem that maybe doesn't seem so hard, but it is. And I bet, I mean, I've been teaching this class for 10 years. Every year I assign this problem, and 98% of people, get it wrong. Usually 2 or 3 kids per class maybe get this problem right, at most. The answer isn't in the back of the book, so okay, let the suspense build. What is going on? Oh, and also this is kind of sad because in class live I would act out a whole thing where it's actually very sad to not be doing this problem live. Oh well. Okay, Zoom school, here we go. Here's what the problem says. I read it aloud. A shipment of 12 microwave ovens contains 3 defective units. Okay? In how many ways can a vending company purchase 4 of these units and receive all good units, 2 good units, and at least 2 good units? This is a crazy problem. So let me just I'm not going to write that entire thing, but we have, sort of taking notes, so to speak. We have 12 microwave ovens. And what the problem tells us is that 3 are defective. I think that's the word they use. And now the question is, let me just make this. A shipment of 12 microwave ovens contains 3 defective units. In how many ways can a vending company purchase 4 of these units and receive all good units? So all good units. B, 2 good units. C, at least 2 good units. So 2 good units, and C is at least 2 good units. Okay, this is so ridiculous. This problem is everything that's kind of difficult about counting problems. Because the problem is written, fine, correctly, but it's written in such a way that it's almost impossible to kind of engage with the problem. After all, what is going, there's about 5 different levels of passive voice involved. There just are some microwave ovens. A shipment contains 12 microwave ovens, we are told. Who is shipping the microwave ovens? I don't know. Who's receiving them? I don't know. 3 are defective. How do we know they're defective? I don't know about that either. And then, subsequently, a vending company, whatever that is going to purchase some of these microwave ovens. Okay, so the vending company is going to be purchasing 4 microwave ovens. Well, okay, I guess a vending company is just some company that buys microwave ovens and then resells them again to other people. I guess the logic of that is that why would any reasonable individual person buy, 4 microwave ovens? That seems like too many, so it must be some company that's going to buy them and then resell them. And, okay, so we seem to have about like 3 or 4 or 5 different actors kind of involved in this problem. There's like the original place that sort of produced these microwave ovens, apparently with some of them defective. Then they've shipped the microwave ovens to someone else who now has the 12 microwave ovens and somehow knows that they're defective. Then a vending company is coming to buy 4 of these microwave ovens. And once again, it's unclear, no one would buy a microwave oven that is defective, intentionally. So it must mean that the vending company doesn't get to test the microwave ovens in advance, which is kind of reasonable. You would just walk in and say, give me 4. And then who knows about the individual people who are going to be buying the microwave ovens from the vending company later. Okay, so this is just terrible. We need to just rewrite in our own mind this problem such that we get rid of all this passive voice and we use kind of active voice. I can't answer this problem until I myself am like in the story and I am going to I'm going to have certain knowledge and other people are going to sort of not have certain knowledge. Okay, so normally in class I would ask for some volunteers and stuff, but okay, we have no volunteers, so I'm just going to do it. So here is what I got. I am an evil, shady microwave oven factory seller. Okay, let's call this store Mr. Rose's Microwaves. Okay, that's a great name. Microwaves. Okay, so I am, in fact, let's just be even more specific. This is the name of my store, and I am just like a store, man. I'm just a store like you would have on the street that sells microwaves. And people can just walk in and just, people can just buy some microwaves. Okay, and, okay, cool. So now, good. So now, here's what happens. I got 12 microwaves. That's it. It's a very small store. And I want to sell these microwaves to various people. Okay, well, I have an employee. Let my employee be Mr. Kirk. Okay, so Mr. Kirk is my my lackey. So let's just say I got like, so I have just like, I don't even know how to spell the word lackey. So I'll just say, Mr. Kirk is my employee. Here's the thing. I'm just crooked. I'm just a evil little businessman who all I care about is profits. That's all that people in business care about. And I'm just gotta sell these freaking microwave ovens. And I have no ethics or anything like that. So I hire an employee, Mr. Kirk, and I'm gonna later on I'm gonna force him to do all kinds of unethical things, and then he is gonna take the fall for it later. Okay, so what kinds of unethical things are we gonna do? Well, I tell Mr. Kirk, yo, Mr. Kirk, go down and check all these microwave ovens and make sure that they work. And so I got these 12 microwave ovens. All right, so Kirk goes downstairs, and he plugs them all in one at a time, and he tries to make microwave popcorn or whatever. And here's what he finds. 9 of them work perfectly, but 3 are defective. Okay, and this story only makes sense if we sort of know which are defective. So Mr. Kirk comes back to me sort of sheepishly and says, this is his first week on the job, he says, dude, Rose, 9 of the microwave ovens worked. I marked them, with like a happy face sticky note, but 3 of them are broken. So that kind of sucks because, then we need to fix them or throw them out or whatever. And I say, ha ha ha, Mr. Kirk, no. Here at my shady Mr. Rose's Microwaves business, we're going to sell these freaking microwave ovens, even the broken ones, and then we're just going to blame it on other people. Mr. Kirk is horrified, and he begins secretly recording this entire conversation. Good. So, for specificity, let the microwaves be named A, B, C, D, E, F, G, H, I can't remember how far I need to go, I need 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let there be J, K, L. These are the defective ones. Okay, so it's like I know that these are working microwaves, and that these are the broken microwaves. Okay, so great. Now, here's what happens. Someone calls up and says, yo, I need some microwaves. Okay, well, it depends who calls. I've been a shady businessman for many years now, and I know that I need to, you know, kind of offload my broken microwaves to someone who is a vulnerable member of society. This is getting pretty dark. So someone who's not going to complain, someone who's in trouble with the law already, or something like that, or someone who I just hate. So so let's do it. Let's see who can. Well, okay, wait. Let's read again. What does it say? How many ways can a vending company purchase all good units? Okay, so let's now change the story and put it into the active voice. So like, you know, Duval wants some microwaves. Wants 4 microwaves. Okay, so great. So now here is the thing about Ms. Duval. She is pretty cool. We like her. She's also powerful and ruthless. So we don't want to cross her because she'll just destroy us. So so Duval calls and says, yo, I need 4 microwaves. And I say, okay. So I tell, yo, Mr. Kirk, go down in the basement and get 4 microwaves for Duval. But, you know, don't give her any broken ones or she's going to come after us. Give her all working ones. All right, so it boils down to this problem, 48 part A, is saying, instead of answering the question, in how many ways can a vending company purchase 4 of these units, of course, if a company has the choice, they're going to purchase good units. So I've now rewritten this problem as, how many ways are there for me, the crooked business owner, to send my lackey, Mr. Kirk, down to the basement to fill this order of microwave ovens for Miss Duval, assuming that we are going to give her good microwaves, Mrs. Duval. Okay, well, I think now it's pretty clear what to do, right? Because when Mr. Kirk goes down, given the order to make sure that the microwaves that we send her are all working, he has 9 working microwaves, and he knows which ones are working and which ones are defective. And so Mr. Kirk's job is to choose 4 of those microwaves. How many ways are there to do this? The answer is just 9 choose 4. So there are 9 choose 4 ways to pick 4 working microwave ovens from the set of 9 working microwave ovens. And what is 9 choose 4? I kind of want like an answer here. Well, it's 9 factorial over 5 factorial times 4 factorial. I think I can just do this, right? Because that's really like 9 times 8 times 7 times 6 over the 5 factorial cancels the rest, over 4 times 3 times 2. And okay, I get some cancellation here, and the 8 cancels the 4. So this is in fact just 9 times 7 times 2, so that's 63 times 2, so that's 126. 63 times 2, yeah. Okay, so I claim that there are 126 ways for Mr. Kirk to fill this order. Okay, who is next? Next is Schaefer. Okay, so Schaefer calls up, and Schaefer also wants 4 microwaves. Alright, so what is now going on is that this says that, so now the question is, the original question as phrased in the book, how many ways are there for the vending company to purchase 4 of these units and receive 2 good units? Okay, so in other words, if you're going to receive 2 good units, then you're going to receive 2 broken units as well. And so, now to rephrase this problem in the active voice, I'm sitting here in my crooked microwave company. Schaefer calls, he wants 4 microwaves, and I say, okay, sure, Schaefer, whatever, coming right up. And then I grab my lackey, Mr. Kirk, and I tell Mr. Kirk, yo, Kirk, Schaefer called. We hate that guy, and he's our enemy, and we really want to screw him over, and we need to offload these broken microwave ovens for a profit. And also, Schaefer's just in trouble with the law, and he's not going to retaliate in any kind of way. He can't go to the police, and so we're gonna stick him with 2 good. We don't want to give him all 3 broken microwave ovens. That's too harsh. We're going to give him a shipment of, he needs 4, we're going to give him 2 working ones and 2 broken ones, and just, you know, screw that guy, and he's going to have to live with it. If he complains, we'll just be like, I don't know, you must have broken them, and maybe he'll offload them to some other customers, and this is how the business world works. Okay, so now the answer to part B is, how many ways? So I've now ordered Mr. Kirk, who's feeling really ethically compromised now, to go down into the basement and to intentionally construct an order of 4 microwave ovens which contain precisely 2 working ones and 2 broken ones. How many ways can he do this? Well, I think this is pretty clear, right? What does Kirk do? He needs to pick 2 microwave ovens from the 9 working ones. So there are 9 choose 2 ways to pick the working microwave ovens. And this assumes that, by the way, that the microwave ovens are all kind of distinguishable from each other in some kind of way. They do have all different serial numbers and stuff like that. Also, Mr. Kirk initially at the beginning of the story went down and marked them all, like the working ones A through I and the broken ones J through L. Okay, so great. Well, there are 9 choose 2 ways for him to pick 2 working microwave ovens, and once he has picked the ones that work, now it is time for him to pick the ones that don't work. How many ways are there to pick the ones that don't work? Well, he has to pick 2 out of the 3. So that's just 3 choose 2, which is of course just 3, right? Because if you're picking 2 from a set of 3, you're really just picking which one, you know, not to pick. Okay, so I think this is pretty clear. 9 choose 2 ways of picking 2 working ones, and for each one of those ways of picking 2 working ones, there are 3 choose 2 ways of picking 2 that don't work. Okay, so now we just need to multiply all this out. Let's see, what is 9 choose 2? It's going to be 9 factorial over 7 factorial 2 factorial, and 3 choose 2, we already said is like 3 factorial over 2 factorial 1 factorial. So, well, okay, what is this? Maybe I'll go this way. So that's just like 9 times 8 over 2, and that's just 3. So that's 9 times 4, so that's 36 times 3. That's like 108. So hopefully that is right. That there are 108 ways to give Schaefer 2 working ones and 2 broken ones. Okay, now comes, so it's possible that you got all that right, but now comes the part that's just so hard. Part C. In how many ways can the vending company purchase 4 units in which at least 2 of the units are good? Okay, this is what's so sort of strange. At least 2 good units. Well, there are a couple ways to do this problem. But first of all, what does it mean to get at least 2 good units? Well, if it means you get at least 2, then it means you get, 2 or 3 or 4. Okay, so now, let's see, how about like load-all calls? So load-all wants 4 microwaves. And here's the thing about this guy, load-all. I'm not really scared of him retaliating, but I don't really like him either. But I don't have any particular, he's not my enemy in any kind of way. So I just tell Mr. Kirk, my lackey, Kirk, I don't really care what you do. Just do whatever. But don't give him 3 broken microwave ovens, because that would be kind of too cruel, and that would arouse some suspicion. So you decide how many microwave ovens you want, broken ones, you want to give him. You can offload, you can try to get rid of 2 of our broken microwave ovens and screw him over the same way we did with Schaefer. Or you can just give him 1 broken microwave oven and 3 working ones. Or you could give him all 4 working ones. That's what it means to give him at least 2 good units. It means to give him 2 or 3 or 4. Okay, so if Lodal wants 4 microwaves and I tell Kirk to give him at least 2 good ones, then one way to do this problem, probably the best way, is to count. Now I'm using the additive principle. I am going to kind of partition the total number of ways by the number of ways in which Lodal receives exactly two good units, or exactly 3 good units, or exactly 4 good units. Okay, so I think this is just hard, partially because exactly at least 2 kind of needs to be sort of mathematically kind of decomposed. At least 2 means 2 or 3 or 4. And since he has to receive a certain number of good units, it has to be 2 or 3 or 4. So these are like independent counts of each other. These are sort of non-overlapping. And so what I'm going to do is I'm going to invoke the multiplicative principle. I'm going to count to figure out the number of ways in which he receives at least 2 good units. I'm going to say, okay, well, let's count all the ways in which he receives exactly 2 units, count all the ways in which he receives exactly 3 good units, and count all the ways in which he receives exactly 4 good units, and then I'm going to add up all those options. Because ultimately we're asking sort of how many ways are there for this to happen, or this to happen, or this to happen. Okay, hopefully I've explained that pretty well. Well, how many ways are there for Lodal to receive exactly 2 good units? Well, if Kirk now decides, well, I'm going to screw that. You don't hate Lodal, Mr. Rose, but I do. So I'm going to, if you've given me some power now, I've become corrupted after 1 week on this job. I'm going to go actually give him 2 good ones and 2 broken ones. And we've already seen how to do that, right? There are 9 choose 2 ways to choose which 2 good ones, and for every way there are to choose which 2 good ones, there are 3 choose 2 ways to choose which 3 choose 2 ways to choose which 2 broken ones. Now, if we're going to give him exactly 4 good units, then we're back to just choosing which 4. So that's 9 choose 4. In other words, the 2 outside cases here are just this is part B and this is part A. So the one we haven't calculated yet is, what if we give him exactly 3 good units and 1 defective one? Well, then there are 9 choose 3 ways to pick which 3 good units we give him, and then there are just 3 choose 1, or you might as well just say 3 ways to pick which 1 broken one we give him. Okay, so if I add all these up, I should get the right answer. And okay, this we did already, so I don't need to redo it. That's 108. This is going to be, well, it's 9 factorial over 6 factorial 3 factorial times 3. And this we did already. It's 126. So what is this? Well, this is going to be 9 times 8 times 7, but then also times 3 over 3 times 2. Because, yeah, okay, I'll leave you to work that out. So what do we get? That's just 9 times 7 times 4. So that is, hopefully I'm doing this right. So that's 9 times 7 times 4, so that's something. That's just like, yeah, 63 times 4, so it's 126 times 2, so that's 252, I guess. Okay, so if I did my math right, I think I did, that number sounds familiar. The final answer is going to be 108 and 252 and 126. And if we add those up, we get 486. Okay, and that just is the right answer to this problem. Okay, so, well, if you've been following along this whole story, then, and you totally get it, well, that's awesome. And this is the right answer to all 3 of these problems, and everything is all good. Okay, unfortunately, you probably got this problem wrong, no offense. What's actually really valuable when doing these counting problems is not necessarily to hear the correct answer, but to hear the incorrect answer. You need to hear what's wrong with what you did. And if until you hear what's wrong with what you did, then you can't really know sort of what really sort of went wrong overall. Okay, all right, so unfortunately no one is here, so I have to just invent what you probably did wrong. But I've also been teaching this class for 10 years, so I kind of know what you probably did wrong. And here is a common student error, which is, I think, very difficult to spot and very difficult to kind of to isolate or something. It's very subtle to explain why this is wrong. So here it is. And I'm going to talk about part C specifically. So we want to pick at least 2 good units. So even if we were thinking about this problem completely clearly, and you had already kind of rewritten the problem to be more active, now here's what's happening. Mr. Kirk is going downstairs, and he has one command, he's working under one directive, which is to make sure that there are at least 2 good units in this batch of 4. Okay, well, Mr. Kirk might say to himself, all right, let's see, what can I do? Well, first, let me put 2 good units in. So there are 9, choose 2. This is Mr. Kirk thinking this out. Ways to pick 2 good microwaves from the set of 9 microwaves. And then, once I've done that, I've already sort of fulfilled my obligation. So the next 2 units can just be whatever. It's irrelevant. And therefore, I just multiply by, well, if I've already chosen 2 microwave ovens, then I've used up 2 of the 12, so there are 10 left. So there are 10 choose 2 ways to choose 2 more microwaves from the remaining 10. Okay. Alright. Well, this sounds very plausible. Just pick 2 good ones from the 9 good ones, and then pick 2 any ones you want from the remaining 10 ones. And, alright, if you calculate this, it turns out that this is just way, way wrong, right? What do you get? Sort of doing 9 choose 2 in my head. That's 9 times 8 over 2, so that's 9 times 4. And 10 choose 2 is 10 times 9 over 2. So that's 5 times 9. And so what we get here is 81 times 20. So that's like a big number, right? 1620. Did I do that right? Yeah, 81 times 2. Okay, so this, the answer I get here, 1620, this is just wrong. I bet a lot of you did this. And, okay, we need to now sort of figure out why this is wrong. Okay, because this is just not the right answer, 486, and so I feel like this just can't be right. Okay, well, and in fact it's much bigger than 486. It's like 4 times bigger, roughly speaking. So, somehow we have overcounted. Okay, let's find, isolate, and explain this error, and then we will learn something. And I just want to say one more time, this subject is really hard, and you're not going to become an expert at it just from this 1 week we're spending on it here at Precalc C. So once again, encourage you to take discrete math, in which we'll do tons and tons of these problems, and with more experience, you'll begin to not make this kind of error that we just made here. Okay, what's wrong with this logic? It sounded so convincing. Well, here's what's wrong. It is when I invoked this multiplicative principle that things went awry. It really is true that there are 2 ways of choosing 2 microwave ovens, and it really is true that there are, if there are 10 microwave ovens that remain, 10 choose 2 ways of picking 2 of those. But it's not true that for every way of picking 2 good microwave ovens, there are fully 10 choose 2 ways of picking 2 other microwave ovens. Because these 2 choices are not independent of each other. And this can be seen kind of with an example. If you're counting, so now I'm going to convince you that you've overcounted and that this approach was invalid by showing how you could have overcounted. Well, okay, suppose Kirk goes down and grabs 2 microwave ovens from the set of good ones. And suppose he happens to pick C and H. Okay, and then he says, all right, I got my 2 good ones, now I'll just do whatever. And then he decides to grab A and L. Okay, Well, that's one way of filling the order, in which it so happens that this person, which is load all, receives 3 good ones and 1 broken one. But another, so if we're sort of counting the sort of a protocol or something, we're kind of counting the number of different things that can happen according to this counting scheme. What if instead, so maybe I want to put like a box around this, because it's like sort of first this happens, then this happens, right? First, Kirk picks 2 ones that work, then he picks 2 whatever ones he wants. But what if instead he first picked 2 good ones, and the 2 good ones that he picked were A and C. And then later, when he was like, you know, following the protocol of just pick any old 2, he happened to pick H and L. Ah, well, according to the counting scheme in which we say that the answer to this problem is 9 choose 2 times 10 choose 2, we have counted these 2 outcomes twice. But these are not 2 independent outcomes. In both of these cases, we have composed an order of microwaves which contains A, C, H, and L. And so we've overcounted, in fact, quite dramatically, because there are other ways to produce this particular outcome, right? There's the outcome in which we first pick A and H, and then pick C and L. And is that it, or are there even more? No, I guess that's it, right? Yeah. So here, in this case, there are 3 times. I have overcounted this particular outcome, the ACHL outcome. I have counted it 3 times in my naive, and it turns out incorrect analysis here. Whereas in reality, this is just 1 outcome. So when you do these kinds of problems, you do have to be careful that you sort of isolate, right? Here, if we need at least 2 good microwave ovens, then we first need to choose like how many of them are going to be good, and then pick the good ones kind of all at once to avoid this kind of overlap. All right, the last thing I'm going to say about this problem is that there's a whole nother way to do this problem that is like even more kind of awesome. And if you're very experienced with doing these counting problems, or if you just happen to think of this great idea, then actually you can do this whole thing very quickly. And I sort of alluded to it already when I talked about what Kirk should do, right? Lodal calls up and says, yo, I need 4 microwaves, and I basically tell Kirk, give this guy just whatever. The only thing you shouldn't do, Mr. Kirk, is give him all 3 of our broken microwave ovens. In other words, to give Lodal at least 2 good microwave ovens really means that I can do anything I want except give him all the broken microwave ovens. So an alternative analysis to this problem is to count all the possible ways of filling the order, which is 12 choose 4. There are 12 choose 4 ways of picking the broken, of just picking any 4 microwave ovens, regardless of whether they're broken or working. And now let's subtract out from the total number of ways the ways which are not allowed. And what's not allowed? Well, the only thing that's not allowed is to give him all broken microwave ovens. How many ways are there to give him all broken microwave ovens? Well, if he's getting J, K, and L, then there's only 1 microwave left, and I just have to pick which one of the 9 broken one, the 9 working ones to give him. So there are 9 ways to give him all 3 broken ones, and there are 12 choose 4 ways to fill the order at all. And so, okay, if you do this, what is this? 12 factorial over 8 factorial, 4 factorial. What is that? It's 12 times 11 times 10 times 9 over 4 times 3 times 2. And okay, this is maybe too much arithmetic for me to do in my head. Maybe not. These cancel, and that cancels with a 5. So 9, so 55 times 9. No, let's do 99 times 5. 99 times 5 is 495 minus 9. And indeed I get 486. This is called complementary counting. This was a lot less work. but you had to kind of think to do this. Okay, so these are two ways of solving 48C. I think I'm out of time now because I think I have to go do a Zoom call. Well, I got 7 minutes. Okay, let's see, what should I do? 49, I guess we're just not going to do 49 or 57. Maybe they're kind of like boring or something. So let me just go and do this 63 and 65. And let's not even do it like, let's not do what you probably did. Let's just do what you should do. Okay. That was kind of vague. Alright. So I'm going to tell everyone to watch this number 48 because I think if you can do that, you can kind of do anything. That's as hard as the counting problems are going to get in this class. I see that this light switch is going to get very dirty. Okay, 63 and 65. 63 says, this is from the other page, page 704. Okay, here we go, number 63. It says n choose m equals n choose n minus m. Okay, and you're supposed to like prove this. Okay, the most mindless way to do this problem is to just algebraically kind of crank it out in total sort of tedium. Is this true? Using my definition, well, it's not a definition really, that's the thing. The definition of n choose m, the sophisticated way to do these problems is to take as the definition of n choose m the number of ways of choosing m objects from a set of n objects. And then one proves that the correct analysis is that this is n factorial over m factorial times n minus m factorial. And, okay, but if I already know that, then what's the right-hand side? Well, the right-hand side is just n factorial over that number factorial, so n minus m factorial, times n sort of minus that number, you know, factorial. But of course, n minus m is just m. So these two are equal, and you know, the most kind of boring way to do this problem number 63, which is probably just what you did, because, you know, what else are you going to do, is to just show that these two algebraically are the same, and we've just showed that. Unfortunately, I've achieved no actual understanding whatsoever by doing it this way. What is the understanding which is contained within this problem? In other words, what does this problem like mean? Well, what it means is that if you have n objects and you want to pick m of them, the number of ways to do that is the same as the number of ways, given n objects, of picking n minus m of them. Well, this makes complete sense, because suppose you have, you know, n students, or, okay, suppose you have n friends, and you need to invite m of them, you know, to a birthday party. Well, you make your list of your n friends, and you got to pick m of them to invite, or you only get to invite m of them. So how many ways are there to do this? Well, there are n choose m ways of picking which m of your friends are invited. But picking which of your friends you're going to invite is the same problem as picking which of your friends not to invite. So if you're allowed to invite only m of your friends, or if you are going to invite only m of your friends, then it means you're going to leave out n minus m of your friends, and that either makes you kind of sad, or if you're a cruel person, you want to, like, you know, intentionally, you know, whatever, but maybe that's actually the most important kind of decision, is not who to invite, but who not to invite. And so you might alternatively solve this same problem by just taking the n minus m friends that aren't going to be invited and picking them. And there are n choose n minus m ways of picking which n minus m friends to not invite. And so that's why these are just counting the same thing. Okay, this becomes relevant in the next problem, because the next problem expresses, this is number 65, and this is the last thing we'll do. This is n plus 1 choose m equals n choose m plus n choose m minus 1. Okay, this is a very interesting and very important combinatorial identity. And we're going to prove it right now. But instead of doing algebra, which is annoying, not fun, challenging, and even if you're successful, you end with a kind of who cares. Instead, let's just talk it out why it is true. And this is what's called doing a combinatorial proof. And a combinatorial proof is a proof in which you prove some counting fact, not by algebra, but by talking out why it is true, using the definitions of these things as being the number of ways of counting certain objects. Okay, and so what we need to do is kind of like understand why this is true. All right, and in class, normally when I go over this problem, if I have time, I you know, let everyone really sort of think kind of deeply about it for a couple minutes, and then we sort of discuss. All right, but Zoom school, no time for any of that. Also, gotta go in like a minute, so we're going to do this kind of quickly. Why is this true? Somehow, given n plus 1 objects, and I want to pick m of them, is the same as the number of ways of picking of choosing m objects from a set of n objects, and the number of ways of choosing m minus 1 objects from a set of n objects. Okay, well let's follow up on the previous story. I have n friends, and I'm going to invite m of them to the birthday party. Okay, great. But then there are n choose m ways to do that, of course. But then I make my whole birthday list. My mom or whatever, dad says, you're allowed to invite m people. You make your list of m people. And then, the day before you're about to send out the invitation to your n friends, a new cool kid moves into town. And this new cool kid is so cool. It's just obvious that maybe they're like from California, and they have like, you know, they know how to skateboard, and they have like big headphones, and they use all kinds of slang words that no one's ever heard of before. This kid, this new kid is so cool that suddenly at the last minute you're like, oh man, I need to invite this new cool kid to my birthday party so I can be cool too. And probably that would also be a nice thing to do because this new person is doesn't have any friends yet in this new town that's not California. Okay, well suddenly what's happened is we have kind of like an extra person to consider. This extra person is like this new cool kid that just moved in from town. And so now I don't really have n friends anymore. I have n real friends plus this new person which I'm already kind of penciling in as one of my friends. Alright, but I'm still only allowed to invite m people, says my parents. So at the last minute I have to amend the list. And I have to sort of consider whether to invite this new cool kid or not. Ah, well then, what is n plus 1 choose m? This is, I'll just say it out loud because I don't feel like writing it down, it is the number of ways of picking the m people that you're going to invite to your birthday party, but now from the enlarged set of n plus 1 friends, which included your n friends plus the new cool kid. And yet, okay, so that, I totally get that. But now, how are we going to do that? Well, there's sort of like one big important decision we need to make when composing this list of who to invite. And that is whether to invite the cool new kid or not. And this addition symbol over here on the right-hand side indicates that some kind of or situation is going on. And the answer is, okay, we're either going to invite the cool new kid or we're not. If we're not going to invite the cool new kid, then it's just the old problem again. I have n friends, and I need to pick m of them to invite, and there are n choose m ways to pick which m friends to invite. But, on the other hand, if I do invite the cool new kid, then I've already put that person, I've already penciled that person in on my invite list. Well then, I still have n friends, but I have only m minus 1 spots. And so n choose m minus 1 is the number of ways of filling in the remaining m minus 1 spots with my n kind of real friends. So this counts, this assumes that we don't invite the new kid. If we don't invite the new kid, then I have m entire spots free for my n friends, and there are n choose m ways of picking this. But if I do invite the new kid, well now I have only m minus 1 spots remaining, and there are n choose m minus 1 ways of filling in those remaining m minus 1 spots with my n friends. And so I add them together because I either invite the kid or I don't. And so I count all the possible ways of making a guest list in which I don't invite the new kid. I count all the number of ways of making the guest list when I do invite the new kid. And if I add them up, that's going to be the total number of ways of making the guest list. Where in reality, I need to pick m slots from among the n plus 1 people which are available. Okay, so hopefully that makes sense, and you can do algebra and sort of confirm that that's true, but that to me is unenlightening. Okay, goodbye!